Today I will share about a new method for predicting open quantum dynamics. So in this talk, we focus on the case where the open quantum system contains only moderate degrees of freedom, while the BAS or the environment is vast and BAS correlation function is not available. And the goal of our work is to extract a classically simulatable master equation of the system from data of measurements performed or measured on the system, but not the environment. And relevant to this purpose, there have been a lot of generic classical algorithms for simulating open quantum dynamics. And the most common one is the plain-Lindenblad equation for modeling the system degree of freedom. It doesn't introduce any extra quantum degree of freedom for modeling the environment. And it captures the environmental effects as a dissipation term. And this plain-Lindenblad approach is efficient, but typically not accurate enough, especially for systems with non-covariant effects. And there are more accurate methods, such as Lindenblad equation for modeling the system, and also auxiliary quantum harmonic oscillators as approximation to the BAS. And this approach, the simulation complexity grows exponentially fast with the number of quantum harmonic oscillators. So it can be made accurate, but it's often too expensive to simulate. And there are also methods like HEOM. It describes the system density operator and also an auxiliary density operators to capture the non-Markovian effects. And again, the capital N here can be very large. And this method can be made accurate, but it's still expensive to simulate. And also, both methods require knowledge of BAS correlation function. That's something about the environment that you may probably not know for experimental systems. So I would say it's difficult for the existing method to strike a balance between accuracy and efficiency. So we ask the following question: is there any data-driven method living in between? We want something that has the same complexity as a plain Lindenblad equation, but can be made more accurate. We want a method that can be optimized on experimental simulation data obtained for just a small unit of an extensive open quantum system, such as a quantum computer. And we want to apply this kind of new method to model real-world systems beyond simple models with non-BCF. So we proposed an approach called data-informed quantum classical dynamics, DIQCD in short. So this DIQCD approach is essentially a variational semi-classical approximation to the exact open quantum dynamics. So it's based on the idea that we can introduce variational capacity to a plain Lindenblad equation while still preserving the physical structure of the density matrix evolution. So we make the Hamiltonian and the dissipation strings in the plain Lindenblad equation flexible. And here I put them in orange here to indicate they are flexible and optimizable on data. And we also make the Hamiltonian to be time independent and stochastic. So this Lindenblad equation becomes the stochastic master equation that can be optimized. And to be more specific, the Hamiltonian here is a linear combination of a static system Hamiltonian and a stochastic term for representing the environmental effects and external control from your experimental scheme. And here, there's time-dependent classical coefficient controlling the stochastic terms, and it's represented by flexible classical dynamical processes parameterized by just a few parameters. And such processes include color noise and thermal molecular dynamics, and etc. The advantage of this DIQCD approach is that the Hilbert space modeled by this approach is not expanded. There's no extra quantum degree freedom. So the extra computational overhead is negligible compared to plain Lindenblad equation. And still, the DIQCD approach can capture different types of coherent noise from data because you have this flexibility and time dependence. And we established the method and program software in a way that this equation of motion, this master equation, can be trained on sparse and noisy measurement data of system observables. And you can train the model like how you train a recurrent neural network. And explicit information of the thermal bath is not required. So we developed the open source Python package called QEpsilon that enable DIQCD construction, training, and simulation. It's publicly available on GitHub with full documentation. And with DIQCD and the QEpsilon package, we show this approach can bridge theories with experiments, and we demonstrate this with 2 case studies showing that we can predict long-term behavior of extensive quantum system based on just minimal local measurement data from measuring the system. And the first case study is about entanglement of molecular qubits. And we show DIQCD can learn from experimental data collected from just one noisy molecular qubit that accurately predict the noisy 2-qubit entanglement dynamics and underlie universal quantum computing. And in the second case study, we focus on quantum transport in high mobility organic semiconductor. And we show that DIQCD can learn from first principle simulation data performed for just one molecule, then accurately predict the experimental carrier mobility in a very large molecular lattice. And today I only have time to explain the first case study, which can be divided into 2 steps. The first step is to construct 1-qubit DIQCD model on noisy data you got from Ramsey experiments. So we have experimental collaborators. They did Ramsey experiments on 1 calcium fluoride molecular qubits under different control schemes, such as spin echo and dynamical decoupling. And they have 24 sparse and noisy data points for 1 qubit. And we train a DIQCD model on this data, and we find out that a single DIQCD model can reproduce all experimental outcomes under their specific external control schemes. And that means DIQCD can capture the decoherence effects, which essentially comes from a very complicated environment. And we can capture it from the time scale from 1 microsecond to 1,000 microsecond. And we can show that applying Lindenblatt equation, even with optimizable dissipation strings, you cannot achieve this. And then the second step of this case study is we generalize the 1-qubit DIQCD model just to train on the 1-qubit data immediately to multi-qubit cases, and we can predict entanglement dynamics under the different device setup without ever training on any multi-qubit data. So what we do here is we generalize the 1-qubit DIQCD model by introducing pairwise dipolar interaction between these molecular qubits. And the dynamical factor in this 2-qubit interaction is further modeled by classical thermomolecular dynamics simulation as auxiliary stochastic classical processes in the stochastic master equation. And this describes the noisy thermal motion of the qubits. And all this require only knowing the temperature of the qubit, the thermal temperature of the qubit, and also the parameters of the optical tweezers. You don't need any 2-qubit data to do this generalization. And we demonstrate that we can use the generalized DIQCD model to predict 2-qubit entanglement dynamics accurately for different optical tweezer setup. And we show the comparison here. So here the solid dots represent experimental measurement of 2-qubit entanglement dynamics. The solid lines are from our DIQCD prediction. And you can see that they agree very well. And for comparison, the transparent lines here are predictions from halfway DIQCD model that does not include this thermomolecular dynamics as a stochastic process to describe the environmental noise inside the dynamical factor in the two qubit interaction. And we fixed it as a single fixed constant. And immediately you see there is a large deviation from the transparent lines from the full-fledged DIQC prediction and also experiments. And that suggests how important it is to model the environmental noise, which is approximately classical in the master equation. So we conclude that the DIQCD strike a balance between efficiency and accuracy for modeling out of equilibrium dynamics of some open systems, and it's especially useful when the measurement data is localized, sparse, or noisy. And a few caveats: for example, DIQCD captures mainly out of equilibrium dynamics relevant to data, but not long-term thermal equilibrium, and that's a common issue of semi-classical method. At the end, I would like to thank my collaborators, Yukai from Princeton and people from Penn State, and also my colleagues at LBL. And I also like to acknowledge the funding from DOE, LBL, and NERSC. Thank you.